Correlation does not mean causation. This is a very popular cliche, but that's just half the truth. The other half is that there is no causation without correlation. Correlation is a necessary but not sufficient condition for causality. Causal AI is fundamentally reshaping the way we approach data science and machine learning problems today. It gained mass interest since Judea published his very popular book, The Book of Why. In this video, we talk about how decision makers should think about causality. We will discuss more technical aspects of causality in later videos when we discuss Causal MMM and experiments. In the book Decision-Driven Analytics by Stephen Pandoni, he classifies data people into two types: divers and runners. Divers are your data analysts and your data scientists, while runners are the decision makers. Both of them have different incentives and motivations when it comes to the way they approach data, and there is always a misalignment between them. The book argues that it's time for runners, who as the decision makers should ideally be the key beneficiary of a good data analysis, to take control of the entire decision-making process instead of just delegating this to the divers and black box algorithms. We believe that causal thinking is the first step in this direction. Causal thinking is when decision makers decide to take full control and responsibility for decisions that they want to take. Let us discuss why we need causal thinking. Here are the 4 key reasons. Reason 1. Data is dumb. This is counterintuitive. We live in a world where we are required to be data-driven. So what do we mean by data is dumb? Take a look at this table. Let's try to predict the value of y as a function of x1. We can run a simple linear regression and we will get an equation that will look like this. Y is equal to 0.3 times x1 plus 31, where 0.3 is the coefficient of x1 and 31 is the intercept. Using this equation, we can predict the value of y for any given value of x1. And if we run this exercise for these 15 records, we can see that our error range is between the values plus or minus 17 for the predicted value of y. Let us try to improve this prediction accuracy by trying to minimize this error. Let us add another variable x2. Now we get a new equation. Y is equal to 0.42 times x1 plus 1.09 times x2 plus 1.93. If you run the prediction again for the historical data, we get an error range of plus or minus 40. This is data-driven analysis. We have added more data and reduced the error. Now let us look into the database and see what these variables are, what x1 and x2 actually refers to. x1 is the height of the person. Y is the weight of the person. x2 is the number of characters in the first name of the person. So we have now created a model that predicts the weight of a person as a function of height and first name. But is first name a good predictor of weight? Clearly not. But data does not know this. This context or intelligence is not available in the data. It is only available with human beings. It is with this realization that causal thinking starts. Along with the data, we need to incorporate causal assumptions for meaningful modeling. Data alone is dumb. That brings us to reason 2. Be mindful of paradoxes. If you torture the data long enough, it will confess to anything. We can prove this by talking about some of the statistical paradoxes. The most popular of these paradoxes is Simpson's paradox. Let us look at this example. This is the survey that was conducted to investigate the gender pay gap issue. For this data of 100 women and 100 men were collected and analyzed. In analysis 1, we can see that the average pay of women is $3,479 and average pay of men is $3,960. So are women paid less than men on average? It's clearly the case. In analysis 2, here we look at management and non-management levels separately. We can see that the average salary of men is less in management level as well as in the non-management level. So what do we take away from this? The same data could be used to make contradictory inferences. What the data reveal depends on what questions you ask. If you ask the question, is there gender wage disparity in the population? You get the answer, yes. If you ask the question, is there gender wage disparity among management and non-management levels? You get the answer, no and no. So it turns out that you could get data to confess to anything even without torturing. Just confuse it with your questions. Data scientists won't know what is the right question to ask. Business decision makers should. Reason 3. Be wary of assumptions. All algorithms, statistical modeling, machine learning, deep learning, all algorithms assume a lot of things implicitly. Decision makers should be aware of all these assumptions. Let us take the example of regression-based MMM. Does not matter if it's Bayesian or not. Let us look at this data. One key assumption for regression modeling is known as I.I.D, independent and identically distributed. We assume that x1, x2, x3, x4 are independent of one another and y is the only dependent one in the equation. We also assume that the distribution of these variables does not change in the future, keeping the model relevant forever. We know that these assumptions are not valid, not in the world of marketing. Problems with independence assumption is this. If X2 is the bottom of the funnel spend, say branded search spend, it'll increase as a result of your top of the funnel spend. Seasonality can drive your revenue, but it can also lead you to spend more in paid spend. This can cause endogeneity in modeling. If X4 is seasonality, then your media spend will be dependent on it. Problems with assumptions of identical distribution. If you use this model for asking what if questions, such as what will happen if I scale my spend in X3 3 times, or what will happen if I go completely dark in X4. These interventions change the distribution of variables that the model is familiar with, making the model drift and its applicability on new data irrelevant. That brings us to reason 4. Reality is not tabular, it is graphical. We have this basic instinct to think of data in tables. For causal reasoning, we need to upgrade ourselves to think of data as a graphs. The word graph here has a very specific meaning. Graphs are made of nodes and edges. They look like a network. Nodes are used to define entities or variables, and edges are used to encode the relationship and the direction of the relationship between these nodes. When it comes to thinking about how seasonality, paid media, bottom funnel spend, and brand equity contribute to revenue, one should think of how they interact between one another. This gives us the causal DAG of these variables and helps us address issues posed by statistical paradoxes that we discussed earlier. Causal structure will reveal the mediators, colliders, and confounders in the data and guides us in applying the right modeling techniques. Here we have a sample DAG. We can see that seasonality drives your revenue and also your investment decision in top of the funnel variables. Demand capture is partly driven by demand generation variables. Brand equity is created by demand generation or top of the funnel spend. In this DAG, seasonality is a confounder and brand equity is a mediator. Besides this, we could also have colliders, which creates closed paths in the DAG. Once we know the DAG, we should try and remove the backdoor paths so that we can achieve statistical independence between the variables. Data is dumb, be mindful of paradoxes, be wary of assumptions, and understand reality as graphical. You can see that all of these are connected. Let me summarize all of this into a brief mental model about causality and correlation. Correlation is not equal to causation. Correlation is equal to causation plus bias. If we can manage to remove the bias, then correlation is equivalent to causation. MMM and experiments try to address this bias in their own ways. While experiments use the technique of randomization to manage the bias, MMM can use techniques such as structure causal modeling to identify the bias and remove them. So over the last 3 videos, we have learned about the need for unified measurement solutions, about incrementality, and about causality. Now let us dive into the world of MMM. In the next video, we will discuss how MMM can help you infer incrementality at scale, how it can help you optimize and plan your paid, owned, and earned media and other control variables such as pricing and promotions, and all of this causally. Let us talk about Causal MMM.